Hello and welcome to yet another video of Cornerstones of Math, and welcome to yet another recurrence relation video. In this video, I will find the general term of the sequence an satisfying the recurrence relation Sn equals 2an plus 3n squared plus 4n plus 5 for all natural numbers n, where Sn is the sum from a1 to an, that is, a partial sum. First things first, let us find the value of the first term a1 since it will be used later. We can use the recurrence relation to find a1 since a1 is equal to s1. So by letting n equals 1, we obtain a1 equals 2a1, then plus 3 plus 4 plus 5, which gives a1 equals negative 12. Next, we need to simplify the given recurrence relation, and one way to do so is to eliminate Sn term. And this is the part where we can apply this basic knowledge about the sum of sequence. When the partial sum Sn is given, you can obtain the general term an by do the following. The first term a1 simply equals s1, and for n greater than or equal to 2, the general term an can be obtained by Sn minus Sn minus 1. So we have this, and by using our recurrence relation, this can be written as first 2 times an minus 1 plus 3 n squared minus n minus 1 squared plus 4, now n minus 1, and that's it because constant terms 5 got cancelled. So we have 2 an minus 1 plus 3 times, this part becomes 2n minus 1. Then we have just 4. So we have 2an minus 2an minus 1 plus 6n plus 1. So we have an equals this, which means that if we solve for an, we have 2an minus 1, then minus 6n minus 1. This is what I would call the simpler recurrence relation, since it does not contain the partial sum. But how do we solve this? Well, in order to solve this rather complicated recurrence relation, first we need to remind ourselves one even simpler relation, which is in this form. An equals p an minus 1 plus q, where p and q are constants. For example, like an equals 2an minus 1 minus 1. The trick here is to change this into the form an minus alpha equals p times an minus 1 minus alpha, where this alpha is constant. Then we can use the fact that sequence an minus alpha is a geometric progression. As for this example, we can easily find out that alpha is equal to 1, giving an minus 1 equals 2 times an minus 1 minus 1. In our relation, we have minus 6n minus 1 instead of the constant term. Still, inspired by previous even simpler example, let us change the recurrence relation into the form an minus fn equals 2 times an minus 1 minus fn minus 1, where fn is now a function of n. By rearranging this, we obtain an equals 2an minus 1 plus fn minus 2fn minus 1. And if we compare this to the actual recurrence relation, we know that fn minus 2fn minus 1 must be equal to minus 6n minus 1. Let us find the polynomial fn satisfying this relation. Let us try the linear polynomial Pn plus q, where p and q are constants. Then Fn is Pn plus q minus 2 times Fn minus 1, so Pn minus 1 plus q equals minus 6n minus 1. If we simplify the left-hand side, we obtain minus Pn plus 2p minus q, so this equals minus 6n minus 1. So if we compare the coefficients, you can easily find that p equals 6 and q equals 13. Therefore, Fn equals 6n plus 13. The existence of Fn means that we can indeed change the given recurrence relation into the form an minus Fn equals 2 times an minus 1 minus Fn minus 1, which implies that sequence an minus Fn is a geometric progression. Therefore, its general term an minus Fn is given by common ratio 2 to the power of n minus 1 times the first term, which is a1 minus f1. Therefore, we can write an equals 2 to the power of n minus 1 times a1 minus f1 plus fn. We have obtained that a1 equals negative 12, and we can easily calculate that f1 equals 19. Hence, an equals 2 to the power of n minus 1 times negative 12 minus 19, then plus fn, 6n plus 13. So we have minus 31 times 2 to the power of n minus 1 plus 6n plus 13. This formula also works for n equals 1. Therefore, we can say that the general term an is given by negative 31 times 2 to the power of n minus 1 plus 6n plus 13 for all natural numbers n. And that's all for today's video. Thank you all for watching. Please don't forget to hit that like and subscribe buttons if you enjoyed this video, and I will see you in another video.